everybody. My name's Sophia. I am a machine learning engineer at a startup in the Bay Area called Curai. And today I'm going to be talking about building your own machine learning data feedback loop. So to start, Curai's mission is to provide the world's best healthcare to everyone. We do this by using artificial intelligence and machine learning with a user-centric focus to provide instant medical expertise that's accurate, trustworthy, relevant, and actionable. So you can think of this as a telehealth platform or a doctor-patient chat application that has AI integrated into the system to scale the doctor's work. We know that AI is particularly well-suited to large-scale data processing, prediction, and automation. And because of this, AI can help scale healthcare via this automation, specifically through giving the doctors back some of their time. According to Dr. Eric Topol, who is the author of Deep Medicine, an excellent read I highly recommend, one of the most important potential outgrowths of AI in medicine is the gift of time. It'll take many years for all of this to be actualized, but ultimately it should be regarded as the most extensive transformation in the history of medicine. So those are pretty bold words, but we have reason to believe that this is true. At Curai, one of the ways in which we use AI to scale the doctor's time is by automating patient information gathering. So in this example, a patient comes in with a chief complaint. Let's say I have a headache. There's a patient pertinent information gathering model that will ask them follow-up questions like, how long have you had the headache? How severe is your headache? Which can then be passed through for diagnosis and treatment. So this machine learning task is going to be the motivating use case that I'll discuss today with regards to building a machine learning data feedback loop. So as an overview, we're going to start by talking about why you should use a machine learning data feedback loop. Next, we'll talk about how to actually build one, so the nuts and bolts of it, from presenting model output to logging your data, data processing, model retraining, testing, and finally integration. And then I'll end with a couple of closing thoughts on ML data feedback loops. Okay, so why should you use a machine learning data feedback loop in the first place? This is basically what a data feedback loop looks like. You have your patient coming in, giving the model its inputs, maybe a headache and a fever. You have a pertinent information gathering model that then you get feedback on these medical questions. So maybe this takes the form of you present these questions to a doctor and they either say, yep, this is a good question, send it on to the patient, or nope, don't use this. And then you use that feedback to retrain your model. But let's start at the beginning. So in V1 of your information gathering model, you're using a couple of data sources to build it. The main one that you're using is a knowledge base, or KB. So this is typically coming from a doctor painstakingly sitting down and writing down all of the symptoms and diseases and forming that into a graph. So as you can imagine, it's pretty time consuming and the coverage amongst all possible symptoms and diseases is relatively low. You might also use patient and provider conversation data to provide additional context and submit that to your model. But at any rate, you've formed now your V1 of your information gathering model and you put it into production. So in this case, a doctor-patient chat application. The problem is that medical models make mistakes in the wild. So this is a real screenshot from First Opinion, a doctor-patient chat application. And the patient's coming in saying, I'm back, baby, want to go see the doctor. They're kind of saucy. I have a headache and a cough and a fever. And then an entity extractor tries to identify the set of symptoms. So it lists 4 of them. And then the patient goes through and says, yep, that's right, or nope, that's wrong. So can anybody, you can just shout it out, see what the mistake was? I think I heard it in the back, maybe. Yeah, so infant is wrong. I'm back, baby does not mean that the patient is an infant. It's just a turn of phrase. So the model's made a mistake here. Here's another example. So the model's asking the patient, have you recently fainted or passed out? And the user says, yep, I have. Syncope is just the medical term for passing out. And then it asks, have you almost fainted? So this is a little bizarre because if you just said yes to fainting, you know that it doesn't make sense to ask, have you almost fainted? But a model doesn't necessarily know that that's the case. So it's not learned something important about these nodes or these symptoms and how they should be connected. So that's the V1 of your model. And we can see here that it doesn't perform particularly well in the wild. We know that under data shift, i.e. when your training data is different from what is actually going on in production, it makes a lot of mistakes. And we know that it doesn't scale particularly well. It takes a really long time to build these knowledge bases, and that's a rate limiting factor. So the main question is, how do we improve the model in a way that scales? One of the main ways that we can do this is through a feedback loop on medical questions. So we made the choice to have a doctor in the loop initially to get high quality medical feedback. So you can imagine you can ask patients, hey, did you like this question? Or you can ask doctors, hey, did you like this question? And because we're using this as ground truth labeling to rebuild our medical models, we chose to use doctors. In practice, what this looks like is that in production, you present the doctor with a choice. They can choose to use or not use a particular suggested question to send to a patient. And if they click yes, you go ahead and send it. And if they click no, you don't send it. And this is a really interesting model because the incentives are aligned. The doctors are incentivized to use this tool because it saves them time with typing. And you might not think that that's a big time savings, but we know that doctors spend 35% of their time on administrative tasks and way too much time doing things like typing or asking the same sets of questions. So it's actually a really big time saver. And if they select no, that's really important negative feedback to our models that the model's prediction was incorrect. So they're using this in production, and we can use their history of their usage data as ground truth labeling, or in other words, as feedback to retrain our models. So we've learned a couple of things here about a data feedback loop. One is that data collection and labeling is often the rate limiting step of ML research. It's time consuming to collect, and it often doesn't perform well under data shift. So that's the status quo. Second, we also know that we're using these models in production and getting usage history from real doctors in real time. And we can use that feedback, that yes or no, as ground truth labeling to retrain our models. This means that the model can get better and better over time using this data and learning from its past history and its past mistakes. So compared to the status quo, we now have a way to scale our machine learning models and iterate much more quickly than we could before. So hopefully I've convinced you at this point that you should use a machine learning data feedback loop. And next I want to talk a little bit about how to build an ML data feedback loop. So these are the nuts and bolts. A data feedback loop, in short, means that healthcare models in our particular use case should learn from their history by harnessing doctor and patient usage data to retrain your models. So this is the high level of what a data feedback loop looks like. One really important note is how you collect your data. So there are two ways you can do this. There's implicit and explicit data. Implicit data collection would be something like you present a suggested medical question to the doctor to send to the patient, and they can either click yes or they can ignore it. So this is lower friction, it doesn't interrupt their workflow, and it's higher signal, meaning that if they say yes, they must have really liked that question. But it's a little bit more confusing for your data labeling. So maybe an ignore means that it was a negative response, it was a bad question, or maybe they just didn't care to use your tool. And the other option is explicit data, which is every single time they have to click yes, use this, or no, don't use this. So that's a lot more straightforward for your ground truth labeling, but it interrupts their workflow. So there's a trade-off there. So in this data feedback loop, you start with your model integrated into your application, and then based on the usage data from your doctor or your patient, you send that forward to a couple of data syncs. From there, it goes to a data warehouse for some amount of data analysis or post-processing. So maybe this is a Python script or some sort of cron job running, and then sent to an output table. So something like a CSV or other data store. Then you retrain your machine learning model, you test and deploy, and you reintegrate. At Curai, we use a lot of different pieces of technology to build this data feedback loop. In the healthcare app itself, we use Docker and Kubernetes. For data syncs, we use things like Stackdriver on the back end, Mixpanel on the front end. We're mostly a Google Cloud shop, so we use BigQuery for data warehouse and Google Cloud Storage for output. Retraining our machine learning models, we use everything from PyTorch to Pandas to TensorFlow. For deploying, we use Helm, and for testing in an online setting via feature flagging, we use LaunchDarkly. So that's a lot of different components. So I want to just focus in on a couple of key pieces. And the first one is the set of data syncs. So we use Stackdriver primarily on the back end for logging what the doctor is deciding to do. So the way that you would actually set this up is you would start with a GCP project with Stackdriver logging API enabled. There's a link down below for a great resource and documentation on exactly how to do that. Second, for your authorized user, you assign the Cloud Logs writer role. So here on the right, you can see a screenshot of how you would do that. It's pretty straightforward. And third, you install the library. So this is a pip install Google Cloud Logging. I should note at this point that we are a Python-based shop on the back end, so all of these examples are going to be focused on Python, but they're very similar in other back end languages. On the Python side, we've gone ahead and made a Flask application to set up our shop. And then we need to configure this Stackdriver logging. So that's what this step is here. The application has some configuration for Stackdriver, and you're just grabbing the Google Cloud logging client. So once that's instantiated, the second thing you need to do is grab that client and then access a particular logger. In this case, it's called NQ log name, which isn't particularly descriptive of a title, but maybe you call it something like doctor selection of model. And then the last thing you need to do is call logger.logstruct, which is actually going to forward your data onto the Stackdriver service. So here you need to collect everything that you would actually need to recreate the decision-making process in real time. Things like the user ID, who actually made the selection, the timestamp or when they made it. Importantly, the model input and output so that you can recreate this environment exactly. Of course, the user selection, any information about your model version. So if we're talking about many different models in production, it's really important to keep track of which one you are working with and your environment. So here's a screenshot of what that looks like on the Stackdriver side. It's forwarding some sort of JSON payload. So here you can see a patient came in with a fever, a headache, and a cough. And the model said, you should ask about a severe headache, or maybe a high-grade fever, or maybe nausea. And the doctor goes ahead and says, I want to ask about severe headache. So that's what the data sync step looks like. And once you've collected that data, you then forward it on to your data warehouse for some amount of post-processing. This involves two primary steps. The first is to scrub your data set of sensitive data. In our case, in our vertical, this is protected health information, or PHI. So things like your name, your date of birth, what your specific medical history is that ties itself to you and your identity. So for example, say one of the things you want to store starts off as, thanks for the info, Miss Sanchez, that's me. Do you also have a fever? And then you transfer that to what you actually care about, which was the name of the symptom. So a KB item or a knowledge base node representation of your symptom named fever. This is also true of other verticals. A really good example is finance or banking. So things like scrubbing data of a credit card number or your personal address. The second thing you do is join your data syncs to form your ground truth data set. So as an example here, suppose you're logging the doctor's choice from your Stackdriver logs, and you have a second data sync from Mixpanel, which is more related to front-end style logging. So things like clicks or an on hover, which you could combine with this other data set to get a sense of what the doctor actually saw and looked at versus what they didn't even bother to take a look at. Once you've done your data post-processing, then you output your data to some sort of table or other data store and use that ground truth data set to retrain your machine learning model. So you could have an entire talk on what retraining your ML model looks like. It's going to be highly dependent on exactly what sort of machine learning you're doing. In our particular case, you can think of it as a graphical representation of symptoms and diseases where the edges are probabilities connecting these different concepts. So perhaps retraining your machine learning model means updating these edges or adding new information that you didn't know about before. Once you've retrained your machine learning model, the last step is to test and deploy. And this might be the most important step of this entire process because we know that one of the primary things we're trying to solve for is that models don't tend to perform that well in production. So the question is, how do you actually test them and make sure that they're going to be better than what you had before? So one of the ways that you do this is the traditional method. So offline metrics, which I imagine most people in this audience are familiar with, you compute on a gold standard test set. In our case, we tend to use a semi-grand test set, which is essentially a gold standard medical test set for diagnostic models. It's really great because different labs or different folks in industry can use it to cross-compare and see how they're performing and how they stack up against other people's approaches. It's a set of 70 to 80 medical cases with a set of symptoms and what the ground truth label is for the diagnosis. So while it's great that you can cross-compare against other people's models, it's not so great because, as anybody who's been to the doctor or taken a kid to the doctor knows, there's a lot more possibilities than just 70 or 80 cases. So to account for that, we also use a test set which is curated in-house by our own clinical experts. So the advantage there is there's a lot more coverage in the possible domain space. So those are the two approaches that we use to calculate our offline metrics and say, okay, in our sort of controlled environment, how is our model performing? The second and perhaps more interesting approach is to look at the online metrics. And in this particular case, by online, I actually mean in production. So when you're actually sending a doctor responses in real time in a real world environment, how do you actually measure how your model is performing? The first way you can do this is by looking at what's called top K accuracy of your diagnostic model in the wild cases. So in other words, you can leverage the fact that a doctor has to fill out these forms and these patient charts with things like what their symptoms were, what the diagnosis was, and compare that to what your model predicted it would be. The second thing you can do is look at user satisfaction in an online model. So this is something like a patient thumbs up or patient thumbs down at the end of a doctor-patient chat. And this turns out to be really important for measuring these in the wild cases. So as a concrete example, imagine that the model is asking a patient, do you have red hair? This is a real example. And that can be a pretty jarring question to ask somebody about the color of their hair or other physical features. It might not make sense in the context of their symptoms. So of course, the patient gives a thumbs down because they don't particularly like that. But turns out from a mathematical and medical sense, this actually makes a lot of sense. We know that in medicine, having red hair might be associated with pain tolerance or anesthesia, but without that additional context, user satisfaction will suggest that that's not a good question to ask. A third way that you can test online metrics is through what we call A/B testing. So instead of just plugging in your new model and totally getting rid of the old version, what you want to do is run an experiment in an online setting. So say you have 3 models, an old one and 2 versions of your new one. What you would do is set up feature flagging so that maybe 33% of patients get model 1, 33% get model 2, and 33% get model 3. And through this way, you can test in an online way which model is actually performing the best. To do this, we use LaunchDarkly ourselves. There are lots of other options you can use. Optimizely is a great one. You could also set up your own JSON file to ingest if you want to do it in a very bootstrapped way. But regardless, all of these approaches are using feature flagging for A/B testing. So for LaunchDarkly, the way that you would set this up on the command line is a simple pip install LaunchDarkly server SDK. And then once you have that on the Python side, you need to go ahead and instantiate your LaunchDarkly client. So here you can see you're setting the SDK key, which is a private key that's given to you when you set up an account, and then you go ahead and get that client. Here is just a wrapper around the LaunchDarkly get variation method. So all this is doing is it's taking in a feature flag that you're trying to query for and a hash, and it's going to give you back the answer. So for example, say the feature flag you want to get information about is your Curai model test. And then you pass in a hash. This is probably going to be a patient or a doctor user ID. And then it's going to give you back an assignment. So some string saying this user should be assigned to model 1 or model 2 or model 3. Here in the model wrapper, so you can see the call to that get variation that we just talked about with a user ID and the model string name. Once you have that string assignment returned to you, you go ahead and you get the actual instantiated model that you're going to call. So it could be as simple as, in this case, a dictionary that you're grabbing that variation from. So that would look like this. Here are your model arms. You got model 1, model 2, and model 3. So in this way, you can do testing across multiple different versions of your model in production. And this is just the LaunchDarkly side of things. If your feature flag is called Curai model arms, and you have your model 1, 2, and 3 that you set up to then link that to your Python logic. So that's testing and deploying. And at the end of all of this, you get the reward, I suppose, which is reintegrating and deploying into your healthcare application. So what this might look like as a final product is, suppose this is the before screenshot. So the user comes in with a cough, a sore throat, and a fever, and the model asks, do you have clear nasal discharge? Yes, no, unsure. And then the new model is going to ask maybe a better question. Do you have a high-grade fever? And in that way, we have a newer version of our model that's relying on usage history for retraining. So that's the data feedback loop as a big picture. A couple of final thoughts. So one topic that's often neglected when people talk about training machine learning models or data feedback loops, especially as it concerns online testing and data collection, is the ethics of building these data feedback loops. So we strongly believe that user trust should come before user usage as a prerequisite. What this means essentially is that the user, whether it's a doctor or a patient, should always understand how and why their data are being used, especially because we're using it to build a machine learning model to make medical predictions. So that is a really important piece. This plays out in a couple of key ways. On the UI UX side, it's about how you actually present this data to the user and explain what you're doing. From an architectural standpoint, it really impacts things like where you store your logs and how you do that in a way that's ethical and compliant. So as an example, perhaps Stackdriver as a data sync is HIPAA compliant. HIPAA being a set of laws, regulations, and best practices surrounding how you store sensitive health information. But maybe Mixpanel is not. And so you always have to be aware of where you're sending this data and what additional security measures you need when building this data feedback loop as it pertains to sensitive health information. So important ramifications both on the UI, UX side and also architecturally. So looking forward, Curai is working on combining the forces of human practitioners with AI to provide quality care at less than 20% of the cost for best healthcare access. We focus on mobile-first care, meaning that you always have access to a healthcare provider 24/7. So doing things like applying a data feedback loop can improve the iteration of your model retraining and ultimately help to provide better question-asking models and diagnostic models to provide high-quality care. And with that, I'll take any questions, and thank you very much.
Hey, I really like what you all are doing. I did have a question. What do you tailor more towards, like trying to, obviously getting it perfect would be ideal, but yeah. Both false positives and false negatives are potentially dangerous in a medical diagnosis. It's not, I don't like the movie you recommended me. How do you handle that? I mean, how do you work with that currently?
Yeah, thank you. Really insightful question. So that actually depends a lot on the subdomain, which is a piece that I didn't really have time to get into here. So for example, when you're building diagnostic models for dermatology, it turns out there are only a couple of treatments for a whole range of dermatology problems. So in that, what you're trying to balance is the risk of different treatments. And so most of the treatments are pretty low risk. So if you accidentally say you have this disease when you don't, and you get recommended a low risk treatment, it's not great, but like it's much better than some other fields. You can imagine as a sort of extreme example, if you tell somebody they have cancer and they don't, and then you recommend chemotherapy, that's obviously a much worse use case. So the short answer is it depends on the subdomain.
Hi, great talk. I'm curious how much of this application works for history, right? Lots of times a patient history is very thorough. Yeah.
So is the question, how does this apply when you're looking at temporal data?
Sorry. Is this for a brand new patient who's just never had any medical history and then the model is trained just on their first one sentence, or is there more personal history involved in the predictions?
Yeah, great question. So there are actually a lot of pieces of data that go into something like this. You have their patient-reported medical history. So my parent has this form of cancer. I take these medications that I have for the last 2 years. There's also what we call episodes of care, or EOCs. That means every time you go to the doctor, that's a separate interaction. And so that is also used as input to your medical model. So you can imagine somebody who comes in who has a history of cancer in their family. You should maybe build a model that's more likely to ask them those sorts of questions, right?
Are there any further questions?
What challenges does this face with HIPAA and high trust and all that sort of stuff?
Yeah, so there are a lot of regulations and best practices surrounding protected health information. The key is a couple of things. First, to always keep in mind that those things are there for good reason. It's to protect patients, and everybody in this room is a patient. The second thing is you just have to be really careful about how you architect your system, right? So this is adding additional layers of security. It's how you do your ops in deployment. It's how you scrub your data. So there's a really interesting field that's just about how can you de-anonymize data and sort of distill that into the data that you need. So yeah, it definitely affects a lot of the work that we do.
Any other questions? Alrighty, I think that's it.
All right, thank you very much.